I want to demonstrate how to do tracing recursion. So I'm going to start with functional number 1. It's good to have a framework for knowing how to solve these problems so you can do them quickly on the AP exam. So I usually start by writing out what function I'm going to be solving for, and then I work through the problem. So this function f1 takes in an integer n and returns an int. So I always like to identify the base case or base cases. In this case, the base case is when n equals 0. When n equals 0, it simply returns 0 and there's nothing else to do. And this is the recursive case. When n is not equal to 0, we are going to return 5 plus a call to the function, passing in n minus 1. And we can see that if we keep reducing n by 1 as we go into this recursive loop, that eventually we'll hit the base case, provided that n is a positive number when we start. So, because we're hitting the recursive case, it's going to be equal to 5 plus a call to f1, but we're going to subtract 1 from n. So if n is 3, we're now going to pass in a 2. So I'm going to rewrite this, but this time I'm going to change this function into its equivalent. So if when n is equal to 2, it won't reach the base case, or it won't meet the base case and equals 0, so it'll do the recursive case. So it'll be equivalent to 5 plus another call to f1 where we pass in 1. And 1 is simply n minus 1. So if n is 2, n minus 1 is equal to 1. And I'm going to repeat this process. I'm going to bring down everything I've written so far, and when I get to the function, I'm going to replace it with what it's equivalent to. So we still haven't reached the base case. If 1 is equal to n, that still isn't equal to 0. So I'm going to, again, it'll return 5 plus f1, where we pass in a 0. Now we've hit the base case, so I'm going to write everything down again. And when n equals 0, it returns 0. So this last term will be 0. Now I can do the final computation, and I have my answer 15. So when you do recursive functions, a lot of times you can kind of make a summary as to what this function is doing. And so to answer the second question, what does f1 compute? Well, you notice a relationship between 3 and 5. So this is really n times 5. Let's solve functional number 4. This one is branching recursion, and so we're going to end up with a tree structure. So we're going to solve for f4, pass in 5. So I'm going to write that at the top. Let's look at our function. So we take in an int n and return an int. Here's our base case. When n is equal to 0 or n is equal to 1, it returns 1. And here's our recursive case. If it's not equal to 0 or 1, then we're going to return the sum of 2 calls, one where we pass in n minus 1 and one where we pass in n minus 2. So you should be able to draw a tree of the recursive calls. So I'm going to give myself lots of space. So I'm solving this one right here. We're going to pass in 4, and then we're going to add that to f4 pass in 3. Let's solve for this one. We're not at the base case, right? And does not equal 0 or 1. So f4 pass in 4 is going to be the sum of, write that again, f4 pass in 3 added to f4 pass in 2. So this one, we haven't reached the base case. So this is going to be equal to function f4 pass in 2 plus function f4 pass in 1. And we finally hit the base case here, but I'm going to solve for this one. So let's go ahead and write this out. And I'll just fill out my tree all the way down to the base cases. So I've hit 2 base cases there. Now I'm going to come up to this one. 2 is not a base case yet. So it's going to be equivalent to F4 pass in 1 plus F4 pass in 0. So all those leaves, basically the ones at the bottoms of the tree, are all base cases. So now I'm going to solve for this one over here. So F4 pass in 3 is equivalent to F4 pass in 2 plus the function called pass in 1. And then this one branches again to F4 pass in 1 plus F4 pass in 0. Now we have base cases on all of the leaves, as they're called. So anything that meets the base case of n equals 0 or 1 is going to return a 1. So this is equivalent to 1, this is equivalent to 1. Those summed together would be equivalent to 2. This one's equivalent to 1 as well. So 2 plus 1, this one's equivalent to 3. These are equivalent to 1. This is equivalent to 2. 3 plus 2 is 5. Now I have to go back on the other side, the right side of the tree. This is equivalent to 1. This is equivalent to 1, which means this function is equivalent to 2. This one's equivalent to 1. 2 plus 1 is 3. Now we have 5 plus 3 is 8. So the solution to this one is 8. And what does this compute? Hopefully you recognize these as Fibonacci numbers. And so we've drawn the execution tree for this function. So why is this function so inefficient? Well, we know it's inefficient because we're making redundant calls. This one didn't need to be called because it was already called here. It's also called here, here, and here. So this is not a great way to solve for the Fibonacci sequence. Let's solve functional number 5. In this function, we see that the base case is when a and b are equal, and a and b are parameters. Next, the recursive call, we actually have 2 options because we have an if-else statement. So if a is greater than b, we're going to return this, otherwise return this. So I'm going to start by writing out the function that I'm trying to solve. And let's begin to process. So is a equal to b? No. Is a greater than b? No. That means we have to perform the else. So that means that our function is going to be equivalent to b minus a is the first one. B is 36, a is 30, so the difference is 6. And then we pass in a. Now our goal is to replace this function with its equivalent. So we're going to trace the recursive function one more time. So in this case, with a being 6 and b being 30, they do not meet the base case. So is a greater than b? It's not. So we're going to be doing this recursive call. So this is equivalent to F5, where we take b minus a, that's 30 minus 6, so that is 24. And we pass in a, which is 6. And we repeat the process. So a is 24, b is 6. They're not equivalent, but this time a is greater than b, so we need to process that function. So we pass in b, and then a minus b. A minus b, 24 minus 6 is 18. And we repeat. So they're not equivalent. That's the base case. A is not greater than B, so we need to do this one. So B minus A is 12 and A 6. And now we process this one. So they're not equivalent to each other, but A is greater than B. So we're going to do this return. So F5, 6 is the first argument, and the second argument is A minus B, which is also 6. We've now reached our base case, and we simply return A, which is 6. So our solution for function 5, or F5, when we pass in 30 and 36, is 6. And you may recognize this function as a way to get the greatest common factor. Let's do string number 1. This function S1 takes in a string S and returns a string. The base case is where the length of the string is equal to 0, in which case we return an empty string. Otherwise, we return the first letter in the string, and then we call the function again and pass in the remainder of the word. So we're trying to solve for S1 cat. We haven't met the base case because cat has a length greater than 0. So it's going to return the first letter plus a call to the function where we pass in the remainder of the word. So I bring this down, and then I'm going to replace the function call with its equivalent. So it would return the first letter of the string, which is A, concatenated with the return value of a call to the function where we return the remainder of the word. So we'll solve for S1T. I'm going to bring these down. So we take off the first letter and return that, concatenated with S1. We pass in the remainder of the word. This will return, since string S, string S is equivalent to a single letter T, and if we were to take the substring at 1, we would indeed return an empty string. So now that this string has a length of 0, we know that that just returns an empty string. So its equivalent would be an empty string. So we can concatenate all of these together and we get cat. So that is the answer, cat. So in essence, this function wasn't very useful. Let's look at the next one that allows us to print. Let's solve string number 2. In this one, we're trying to solve S2, where we pass in cat. This function, its base case is implicit. So it's implicit in the sense that when the length of S is equal to 0, we do nothing, because this method returns void. So the base case is that the string has a length of 0. So the recursive case is that the length of the string is greater than 0, in which case we're going to print the first letter, and then we're going to make a recursive call with the remainder of the word. So with these, I like to set aside a little space to keep track of what is printing. So as I process this first function call where I pass in cat, the length is greater than 0, and so I have to print the first letter, which would be C. Then I have to make another call to S2, but I'm going to pass in everything but the first character. And we repeat the process. For S2, the length of my string S is greater than 0, so I print the first letter, and then I make another call. Pass in the remainder of the word, which is T. I have to print the t, and then I make another call to the function. This time pass in an empty string, and this is the base case. The function does nothing when the string has a length of 0. So we're finished with this one, and the printout is cat. For string number 3, we have a function s3 that takes in string s and returns void. The base case is when the length of the string is equal to 0. So otherwise, if there are characters in the string, we would make the recursive call to s3 with the remainder of the word less the first character, and then we would print the first character. So note that the recursive call comes before the print. This is important because it may have the result of printing things backwards. I'm going to write out the function that I'm trying to solve, which is s3cat. And what do? Well, we haven't reached the base case. The length is greater than 0. So before I can print anything, I have to make a recursive call to s3, pass in everything but the first character. And when this one gets called, I can't print anything unless I make a call to s3, pass in the remainder of the characters less the first one, which is just passing in t. Still, I can't print any letters unless I make the recursive call to s3, pass in empty string. Now I've gotten to the base case. The base case is when our string s has no length, has a length of 0, has no characters in it. So basically this one does nothing. So that means we have to return control to our function when s equals t. So in this case, we're going to print the very first letter. So over here is where I'm going to keep track of things that I print, and I would print the T. Now this one's done, and my control returns up to this one. So now I have to execute the print statement here. Well, the print statement here prints the very first letter of S, and so that one's finished. It's off the stack. And then I return to the very first call. The first letter of cat is C, and then that function is finished, and we're done. So this has the effect of printing our letters in reverse. Let's solve arrays and array list number 1. This uses an array, and we're going to use this array down here. And it also takes in an n, which appears to be used as an index. The base case is when that index n equals 0, in which case we'll just return the very first element in the array. If we don't hit the base case, we do have to come up with a value for m, which is determined by recursively calling our function a1 and passing down a lower value of n, so n minus 1. After we determine the value for m, we determine which one is greater, m or the value in the array at n. So let's begin by writing out our function call. So we pass in our array, I'll just call it a, and we pass in n, which has a value of 3. Now, this is not the base case because n is not equal to 0, but we will have to determine the value of m. And m is equivalent to the call to a1, pass in the same array, but this time we pass in n minus 1, which is 2. So I'm going to take this call over here and determine the value of a1 for this set of arguments. And when n is 2, we haven't reached the base case, so we will have to determine the value of m. And m is equivalent to a1, pass in a, pass in 1. So I'm going to bring this over here. So we're looking for A1, pass in A, comma 1. Still haven't reached the base case, so I have to determine what the local variable m is. So A1, pass in A, pass in 0. Well, 0 is the base case. So if I look at this base case, then I just determine I have to return the value at index 0, which is just this one. So m in this case is equal to negative 3. Let me write that in a different color. Negative 3. Now, I'm to this point in the code where I now have an m which I can compare with the value at n. And this is n right here. So if I go to a at index 1, that's equivalent to 1. So which is greater, 1 or negative 3? Well, 1 is greater. So that is what is returned by this function. This is equivalent, this is equal to 1, which means up here, m is equal to 1. So now I can look at this value for n and look at it right here. So that is looking at the 4. So which is greater, 4 or 1? Well, 4 is greater. So this one is equivalent to 4, which means now I have an answer for this m. So m up here is equal to 4. So now if I look at this value for n in this first call, that would look at this element right here, which is a 2. So which is greater, 2 or 4? 4 is greater. So this is equivalent to 4, and that is our answer. Let's solve arrays and array lists number 2. In A2, it takes in array A, which we'll be using this one right here, and it takes in a value for n. So the base case is when n is less than or equal to 0. Otherwise, if n is greater than 0, we are going to have to add something into A and then make a recursive call. Because we're modifying the array, it may be a good idea to write it. So I'm going to write it up here and then modify it as I need to. So my array is 1, 2, 3, 4. And I'm going to write the indexes below it. Now I'm going to make the call to A2. So A2, and I'm just going to use A for my array. And we're going to pass in length minus 1. So this array has a length of 4, so length minus 1 would be 3. So when I pass this in, n equals 3, so we didn't reach the base case, so we have to process this change right here. So we have to go to 1 less than n and add to it the value of n. So we're taking this number and this and adding it to this number. So 3 is no longer 3, but instead it's 7. Okay, then we have to go to the next recursive call. So A2, pass in A, pass in n minus 1, which is 2. Now we have to process this statement. So we go to n minus 1, which is 1, and to it we add a at n. So this one is going to be changed, and it's going to be the sum of 7 and 2, which is 9. Now that statement is finished, and we must make the recursive call. To A2, we pass in A, we pass in 1. So we haven't reached the base case. 1 is greater than 0. So we have to process this assignment change. So that means this value is going to change, and it is going to be the sum of 9 plus 1, which is 10. And then it's ready to make the recursive call. So A2, pass in A, pass in 0. We've now reached the base case, and we do nothing, and we're complete. So if we wanted to write the final outcome for our array, it's 10, 9, 7, 4. Let's solve for printing number 1. P1 is a recursive function that prints something. It returns void, takes in a value for n. The base case is when n would equal 1 or less, and the recursive case is when n is greater than 1. We see that there's 2 recursive calls, so we know that this will be a branching function, and in between the 2 calls is a print statement. So I'm going to give myself lots of room. P1, pass in 4. So I start by making a recursive call to P1, 3, and I don't hit the print statement until I finished off the recursive calls. So P1, 3 is going to have to call P1, 2, and P1, 2 can't print anything until it calls P1, 1. Now this is the base case, and it will do nothing. But it does allow for this function to now print 2. So I'm going to write this in a different color so we can identify that as printing a 2. This function then makes another recursive call to P1 pass in 1, which means control returns up to this function, and it is able to print itself and then make its recursive calls. And this one can't print itself until it makes its recursive call. That's our base case, which does nothing. Now this function can print 2. It makes its second recursive call. And this one's finished, and we go back up to where n is equal to 3. That one's finished as well. So now we go up to this one. It's able to print itself with the 4 and then make recursive call on this side. But we can realize that this recursive call right here is going to have the same outcome as this branch, this subtree right here. So if we were to summarize this, we could just say that this function we know is going to print 2, 3, 2. So we can just kind of stop right there. So over here we'll answer our question. What does P1 pass in 4 give us? It gives us 2, 3, 2, 4, 2, 3, 2. Now it asks us what P1 pass in 5 prints. And we knew that that would have to call P1, 4, then it could print its own 5, and then it would have to call P1, 4 again. Well, we already know what that prints. So we don't really have to do all these extra steps. We know that this one is equivalent to 2, 3, 2, 4, 2, 3, 2, 5, and then 2, 3, 2, 4, 2, 3, 2.